many thanks to everybody who decided to be with us. And today our speaker is Professor Vladimir Mityushev. Professor Mityushev is a professor at the Kraków Technology University, Kraków University of Technology, and he has a long experience in mathematical modeling, in simulation, and also he is expert in modeling of random structures with many implementations, especially in area of bioinformatics. This area probably is the most interesting for us. And he has spent many times also in France conducting research. So we have Professor Mityushev today with us. And if you need to ask questions during the talk, it is possible. Of course, we will have, as usual, we have a questions and answers at the end of the talk, and we will have a discussion at that time. So, Professor Mityushev, the screen is yours.
Okay, so thank you very much for this presentation. The title of talk, Analytical RVE, Representative Volume Element Theory of Dispersed Structures and its Application. So it's an abstract of the talk which published in SanoScience webpage, and I would like just say about the keywords. So I'm interested in some analytical method, and I will present this mathematical method which describe interactions among inclusions element in dispersed heterogeneous media. So I use analytical theory of representative volume element, and I will try to apply the method to image analysis of pictures related to classify of glioma structures, and present a mathematical method which is mathematically theory is very complex, but application is very simple, and I will explain some important steps why and how we can use the proposed method. So the method is summarized in this book. Maybe it's related rather to metamaterials, but it's also include biophysical applications. It's the previous year book. Okay, so typical figure which I would like to present, it's microscope image of cancerous mouse brain biopsy. So it's an image, and for my, let me say, mathematical analysis, it's important to first to read this picture and see this inclusion cell glioma, and I will consider this picture as a heterogeneous structure. So my previous results are related to material science and others. So that is why medium heterogeneous medium is a proper term for consideration of this brain biopsy. Another picture, it's cancerous tissues presented by Pablo Losa in a recent workshop in Barcelona. So it's also, let us look at this like a picture which present a heterogeneous media. Well, so what is the method to study this picture? When my analytical method is effective and when. So let me have a picture, but of course it's just a present one picture, but it's necessary to consider, I don't know, hundreds, 1,000 pictures in order to make statistical analysis. And let an medicine expert cannot certainly say about the illness. You see on this or the first picture. So if a medicine say, okay, I see here cancer, it's some stage, so no problem, my method is not useful. Yes, but if we have not clear situation, when we have gradation of cancer like this, and expert hesitates, in this case, it's possible to apply the analytical method. Well, what is a known method related to image analysis? I met papers, Monica Pyrek from SanoScience, when the straightforward high advanced analysis is developed related to machine learning and network. So we observe something, and let us think that an expert cannot say something, maybe machine learning could say something useful. So, but anyway, and in the first case of expert and in the second case of straightforward processing of image, we could say about observation, and maybe it's enough to see and say, yes, we have such a state, but sometimes, not sometimes, but usually it's maybe gradation and so on. So let me explain some hypothesis condition to apply analytical method. First, we have this picture, and the considered process, so it's a picture, it's an instantaneous, it's a not a dynamic picture, but let us look at this picture, and we consider it a process as at that moment, and that this process is governed by physical equations. So this is important. So we are based on physics, not only images, not only colors, geometry, but on physical equations. Second, in the framework of this physical equation, elements on the picture, I mean here these cells, you see, they maybe to show in such a case, in such a manner like this, these elements interact each other in the framework of physical field, physical equation. So if we have these assumptions and consider this heterogeneous picture from the general point of view, then we have additional features. I mean, here I come back to straightforward image analysis and straightforward network analysis, machine learning. So, but in such an approach, we have an additional physical features if a process is going on in accordance with physical laws. So I would say that it's, I don't know about chemistry, maybe chemistry, if it is related to diffusion, then chemistry is physical process. Well, but in general, of course, we have also chemical reaction, chemical change, we cannot capture it by the proposed theory. Well, let me go further. Just, I come back to this regime. And about equations. So here I propose to a universal mathematical modeling table of physical phenomena. physical phenomena. It's from my textbook, Introduction to Computational Analysis. But let us look at this. It's a known, more or less, table. First, I saw this table in Weber book in electromagnetism in 1950 about this, and after it can be completed and considered in the universal manner. So if we have some equation like this, so I hope you see when I show this text. So it's Gavin equations, and then the same equations describe different processes: electrical conduction, dielectric, magnetism, next heat conduction, diffusion, flowing porous media, unseen plane elasticity. Also, it's possible to describe plane elasticity. And I would like to add coupled process, for instance, diffusion with heating. So let us come back here. I consider linear equations, and if a process which is going on this picture is governed by diffusion, electromagnetic waves, by dielectric permittivity, dielectric permittivity, and so on and so on, then this process allows to find new geometrical features which are not captured of simple observations. Okay, so how I do it? I do it in the by using the homogenization theory. So this field, heterogeneous field, has properties on different scales: micro scales, mesoscales, and macro scales.
Excuse me, may I? Because it seems that we have a question from the audience.
Yes, please, because it's in chat. I don't see chat, so please say.
We have a question from the audience. I think that we have Piotr Gadaś, who is trying to ask the question. Well, you can type your question on chat if you do not like. Okay, so I will try to. I will observe what will be presented in the chat, because
I don't see the chat.
Raised hand, and it seemed that it is the kind of, let's say, asking for a question, but it disappeared, so it's okay. So please go on.
Okay, so thank you very much. So I don't see the chat, so please.
I'm trying to observe it.
Ask the question by voice, okay?
Thank you.
So this is a picture, idealized picture, to summarize the homogenization theory. We have a representative cell of some elements here. For simplicity, I consider just circles, so two-dimensional picture. I don't go to three-dimensional, more complicated story, but let us consider in the simplest way how it's possible. And according to the homogenization picture, the properties, macroscopic properties, are defined by a representative cell. So what is a representative cell? So it's a separate, very interesting equation, but we have this cell, a representative cell. So we work this picture. We have a periodicity, so it's double periodic. Double periodic is necessary to properly compute macroscopic properties and mesoscopic properties. So it's impossible to consider a finite picture and just consider some representative. So we have to consider double periodic system. Okay, so what we consider, which problem? It's let me say in the language of permittivity, or maybe permittivity may be complex, or maybe in conductivity, heat conductivity. Let me say about conductivity. So U and UK are temperature, distribution of temperature, and this is heat flux. And we have on the boundary the ideal contact. So this is equation of temperature, this is equation of heat flux. So then we have to find function U and UK, harmonic, satisfying Laplace equation, maybe other equation, little bit Laplace equation in all this domain. And here we have boundary condition, and also we have an external flux which is going through this media. So it's a like boundary condition, external condition. So here you see the coefficient, which is coefficient for determination of heat flux. So here I take 1. So it's just for normalization, because it's possible to divide, if we have here a constant, by this. So this is epsilon k, is a ratio of heat conductivity of inclusion and a host material. So if we introduce this, then we introduce another contrast parameter. So contrast parameter is difference between conductivity of inclusion and the host. Host is equal to 1 conductivity, and divided by plus. And this is contrast parameter depends on physical constants. So we have this problem, it's boundary condition, and the problem can be solved by alternating method of Schwarz. What is the method of Schwarz? Here, the history about this method. So if we consider two inclusions, two different small elements, then we are interested in the interaction in the framework of this heat conduction field or other field. So it can be represented by equation 3, here equation 3, which it's a balance of, here the balance of temperature, Here we have temperature in the inclusion GK, and this temperature is related to rho physical parameter. Fk geometry is an integral operator, I don't write it here, which is self-induced term. So UK, self-induced term UK. So if, for instance, UK is a circle, it is equal to 0, no self-diffusion. And here the term of operator with all other inclusions, so interaction with each other, and U naught is an external here temperature, external temperature at infinity out of the picture. So this is an equation which can be considered as an equation with operator interaction between inclusion. And the method of successive approximation, if we apply for this equation, so we will consider a field in the inclusion K like external field U naught plus rho. It's a first contrast parameter coefficient, physical coefficient, when we have first order intersection. Next, we have rho square and second order intersection. And so on. We have an infinite series, and how this intersection can be constructed. It can be constructed like this. So it's, for instance, we are interested in the field here. So this field contains a lot of terms and infinitely many terms, but for instance, terms which influence of J4 through J2. J2, the result impacts on J3. J3 inverse impacts to J2, and so on. So if we, from this inclusion, in many ways, we can come to first this inclusion, and this is the part of this operator. So we have here an infinite series of these inclusions. So the real theorem about convergence, it's a pure hard mathematics, but no, just believe me that the method under this condition conversion. Okay, so next, if we apply this method constructively for circular inclusions, then we see that we have that Eisenstein function arises. What is the Eisenstein function? Definition is written here. So it's omega 2 and omega 1, omega 2 are the translation vectors of the parallelogram. This. So it's omega 1, it's omega 2, expressed in complex numbers. So here we have argument Z minus all the periodic translations. So M1, M2 translations over the plane. And in the power minus P. P is equal to 2, 3, 4, and so on. And we obtain some object which is called the structural sum. So it's let me write some simple sum. E2 is equal 1 divided by n squared. N is the number of inclusion per cell. So here we have a double sum over differences of all inclusion, first with second, first with third, first with another, and so on. Here the double sum over all inclusions. So this is the structural sum E2. Next sum E2, and so on. So actually it's a discrete multiple convolution of the Eisenstein function. So what is E2 is like sinus, cosinus. This function is related to P-Weierstrass function, so it's implemented to any package, any good package like Python, Mathematica, anywhere. So you just take the coordinates of points, write it cont, and compute this sum and many, many others. So why this sums is important? Because application of this series yields, after averaging, the effective permittivity or conductivity tensor. So it's equal to I, the unit tensor. Yes, so because you remember we had normalization, that is why we have, this is like zero approximation, we have only host. Next, plus 2 rho. Rho is a physical contrast parameter. F is a concentration of inclusion. Here I write a formula just for simple case of two-phase heterogeneous media. And next, coefficients with power of F, concentration, which are expressed in terms of structural sum. So let us look at this formula 10. So we have a decomposition of effective tensor through physics. Physics is here in rho. Here also in coefficient rho, like this. And geometry. And geometry is here. It's pure geometrical object. So let us come back here. We have after some normalization, some special function, Eisenstein function, calculated as the difference of points. So it's convolution. No any physical terms here, just geometrical parameters. So that is why formula 10 is important. So we have some decomposition of physics rho. geometry, also F a special parameter, geometric concentration, so it's power series in F in concentration, and geometrical sum, look here. And that is why I use this Eisenstein function, because it's I solve the problem by Schwarz method. I begin to compute all the interaction, introducing the computer, symbolic computation, put the button, and I have this function. That's all. It's not my guilty that we have such a function. It's objective. Let us look at this objective. It's a deep theorem, because we may look at these structural functions, structural sums, pure geometrical, and look at this formula as a linear combination of structural sums. So if we have infinitely many structural sums computed, we can, with special coefficients, like here, numbering and raw physical coefficient, compute the effective properties of this structure. So I put the button in the computer, and I have formula with any precision what I want. It should be said that if you use autocorrelation function or the two-point correlation function, then we stop here. So all popular formula stops here. These terms are not known, so these terms are written only here, and I can proceed this process and calculate everything. Okay, so it's a computation, first point computation of macroscopic properties, and hypothesis is like this. So if we have two different cells with different properties, we have different effective properties. Well, so we can compare these properties, and after say, okay, so it's one with different frequencies. Frequencies, I mean permittivity, electromagnetic equation, permittivity tensor. But it's possible to consider only on the geometric constant. So we look at the picture, and we have two elements, two geometrical center, A and A prime. Next, let me compute the structural sum for this geometrical picture. Of course, it's necessary to think about statistically many pictures, but let it be so, let just one picture. Next, we compare with this picture or with this class of picture. So we compute another sum, because we have another location of the centers of inclusion. And as a result, we have here 1-point function, here we have 2-point correlation function, and so on. So actually, if all these constants coincide with the constants of this, then statistically these two pictures are the same. So it's a classification. So I don't say now about statistical classification, machine learning classification, but it's we have pictures, we have papers, and we can apply this. So this is a method related only with the properties of these features. And about these features are based on the physical process. It's not observation. So if you have observation, if you, for instance, observe the sun, okay, so the sun, you say, okay, so its intensity now here, so you have some spots on the sun and so on. But if you know that the motor is nuclear reaction, you have some feature like this, which is not acceptable, acceptable in observation. And another point of view, so if in observation, usually you may find a good constant like energy in some sense. So it's impossible in this point of view to describe a heterogeneous material from one constant. Maybe it will be very, very important and everything will be clear. But for precise description of this material, you need an infinitely many constant. Of course, you may truncate the system and compare, classify by a vector. Well, so what is the idea of this method? So if we have this inclusion, we have centers points of these cells. We compute a vector, of course, finite vector, and next we say that another medium, if this medium in statistical sense has closed to this vector, then they are has the same gradation of illness, or maybe the same health, or maybe, you see, this is the main idea, just an idea with simple computations. Okay, so this method is related to correlation function, as I said, but it is possible to create just 2-point correlation function. 3-point and so on, it's a problem. It's a problem for computational. Here I avoid computational, this function, and give a result through Schwarz method with structural sum. So actually, this is the way to use multi-point correlation functions, and multi-point correlation functions describe all the interaction between inclusions. So if the hypothesis of this theory, if these inclusions cells interact, then we must use multiply point correlation function related to some physical process. Okay. So another interesting point, it was developed for three-phase materials. Here I present black, blue, and host three-phase. So we calculated interaction between two sets of two sets for clouds, usual clouds, because clouds, it's and a paper is published, and we noted, for instance, the following way. So we calculate structural sum epsilon1 for black points. Next, we calculate for blue points, and we calculate for joint union of all these points. And what we see in clouds, we see some physical correlation between functions, between different phases like this. If we consider black points, we have the degree of anisotropy. Anisotropy is a, let me say, it's a constant structural sum E2. It's a fine result that, look here, E2. The result is the following. If this constant is equal to pi, exactly pi, then this material is macroscopically isotropic, necessary condition for macroscopic isotropy. So if it is not pi, so it's anisotropic. And what we had for clouds we have blue is more or less isotropic, but not. Black is also not, but together this set is anisotropic. So this is influence of the white of the blue set onto the black set. So black set it's an interaction between two sets, not only one by one, this element, this is element. So these sets allow to find intersection between total sets of two components, black and blue, and and ask the question, do they interact or not? So in this case of clouds, we found this interaction. So this is another application, but it was made only for usual clouds on Baltic Sea. Okay, so I would like to propose this theory, which bridge classical harmonization theory for random material and application maybe in diagnostic and classification glioma structures, not only clouds and other structures. So if we have a set of corresponding picture, if I haven't, but if we have, we can analyze this picture. And after, of course, we are going, because today I said about deterministic picture. We just consider two pictures, but it's classification. So we have to consider from statistical point of view, machine learning classification question. And after, of course, it's interesting to compare with specialist and medicine. So it's my talk, it's over, and I haven't a result how to classify this. It's just an idea how to do it together with specialists in medicine. So thank you very much for this.
Well, many thanks for your talk. As I understand, we have a kind of approach to possible analysis of medical images. So, as I understand, we have an approach in which you may you have a kind of a mathematical formula and mathematical models which give a chance to have some conclusions about interaction on different elements of the structure on image. And then it depends on a specific, let's say, area, how to interpret all this. Well, I hope that people involved in analysis of medical imaging will take part in this discussion and will.
Yeah, that's right. Yeah, you summarize exactly what I want to say without. So I would like to say that it's theorem and theory, mathematical theory is very complex to prove the convergence. That it's really a basis of some, but application is very simple. So if you have function implemented computation, you just compute these sums and say, okay, so we have the classification vector. Thank you.
Okay, so it's let's say a request for discussion to participants of this seminar. Well, so it is about your talk was mostly about, let's say, introducing this for medical computational medicine for analysis of medical images. But what about experience with other pictures of this type, let's say from, I don't know, structures of different materials systems? Have you implemented this, or it is also an open proposal?
Yeah, if you ask about material science, it was done from 2000 to up. So it's done. So it's medical pictures. It's a new point where I want to work. I want to cooperate. For material science, the theory is completed. So I would like to say, so for instance, random media from material science, it's clear from this point of view. Not I would like to say about it's very popular finite element method, and it seems that it's possible to put the button and calculate everything. Yes, it is so, but if you consider a deterministic special structure with special constant. But for instance, you couldn't capture interaction by finite element method. In material science, it's done. Because here I presented hypothesis. We consider a medical picture, and the cells in inclusion interact each with each other. But in material science, it is so. If we have heat conduction, yes, we have equation of heat conduction. If we have porous media, yes, we have porous media. If we have elasticity, so we have inclusion which interact through the host to each other, its hypothesis is going from this point of view. So it's done, and it's done, let me say, many years ago. There are some difficulties in three-dimensional cases. It's not mathematics, it's not so constructive. Because here in the plane we have elliptic functions, very well developed Eisenstein function. It's just like a sinus, a cosinus, not more. So if you use Fourier series, you may use this. It's extension of one periodic function to double periodic function. Well, so yes, in material science, yes. In cloud is also, I suppose it's close to material science because it's fluid dynamics, and we have, let me say, Reynolds equations, Navier-Stokes equation. So, and Navier-Stokes equation in linear approximation is equivalent to elastic. So it's going to this universality table. So that is why, so if in linear approximation, so it works. So I have to say that non-linear processes are not captured because Schwarz interaction assumes linearity. It's possible to, you see, it's possible to go, but it's, I don't think that it's mathematically abstract good theory because we want to have linear combination in vector space. And if you have non-linear equation, it's difficult to say about a representative like a combination, linear combination. So it's much more complicated. But in linear material science, yes, it is done, and I suppose it's complete. And it worked very well.
I understand. So it's, I think that the main idea is that all of these diseases will manifest in such a way that in a given part of a human body there will be a change in the structure, yes, and some material which could be simulated as something which is homogeneous becomes build of not one component, but there is a additional component, and we are using this additional observation of this additional component to understand how it happened, yes, and discovering the, let's say, what was the reason for this. We may find, let's say, what type of disease it is, as I understand. So it's you assume that description, mathematical description of some processes like this heterogeneous materials will be the same as here building or appearance of a heterogeneous structure. And the question is to find equivalence between all of these values, parameters which were used to describe these heterogeneous structures here with, let's say, biological structure, yes?
Yes, yes. Thank you very much. Let us come back. You say multi-phase media. Yes, majority of my formulas which I present was for two-phase media, but at the end I said that it's possible to apply to three-phase, blue, black, and the host. Of course, mathematics is very simple to write for any multi-phase media. It doesn't matter. Next, yes, that's right. Heterogeneity is the most point. If a biological medium is heterogeneous, and if it's suggestion that we have interaction in the cell between different cells, yes, the interaction, physical interaction. I don't know about chemical interaction. Maybe you see, maybe one say to other, "Hey, go, come together. Let's go to." It's another information theory. No, I mean exceptionally physical classical process governed by classical equation. Then, yes, then I can distinguish some elements, geometrical, structural some, which describe all the interaction between this element, one by one, set by set, and so on. So this is that point. So thank you very much for this point. Yes, it is so.
Well, so I understand that it could be somehow a process which after image analysis can go on and to be process which can, let's say, different structures can be assigned to, let's say, different type of villains or something like this. Well, it's I think that it is something what is ruled by mathematical equations. So it's always you have, especially in medicine, where some medical doctors required not only information what to do, but why. So maybe for this reason, it may be something important because it gives explanation why something happened. Yes. Okay, so I will try to look at the list of participants and see if
maybe I comment. Thank you very much. You say that how it looks, but you see, actually, I don't ask why one cell becomes another cell. No, I just look at the geometry and just say result. And why it's I suppose that they interact by physical equation. That's all. But I don't know what is heat, electromagnetic. So it's I don't know the process. Process is governed by so geometry is here. So it's not exactly that you said that why. No, I don't say why. I say I see, for instance, after analysis that they interact, but why I don't know. You see.
Okay, we have Wiesław who is going to take part in discussion. Wiesław, please go on. You are muted.
Can you hear me? Okay.
Yes, thank you.
Hello, thank you for your talk. Yeah, you mentioned about potential application for glioma, but I believe that the method might be potentially useful in general in histology. For example, for the brain, I believe there are more than 100 types of tumors, and those tumors need some grading. So I think that applicability is very, very wide. This is one potential topic. Another is recently there are several big projects which aim to classify brain cells. So also maybe there is another potential to use your method to distinguish different brain cells, because normally we say, oh, these are just neurons and glial cells, but it's not so easy. So I think that this might be the second area of application. The third one might be not so obvious, but I think it will be coming sooner or later. If we want to distinguish different types of synapses. And for example, at Jagiellonian universities at Solaris, they have capabilities using cryomicroscope to generate images at this kind of resolution. So I believe this also might be another source of nice images to try the power of your method. I don't know if those comments make sense, but this is what it's my thinking. Thank you.
Thank you very much for this great proposition. So maybe you see I'm lost in many things what you said, but maybe let us discuss separately. Maybe maybe I write you email and.
Don't feel lost, because I also was lost when you presented your method. But of course, I'm just judging based on some general features, yeah? And of course, my comments are mostly about the brain, because this is my area of interest. But again, cells, tumors, and synapses in brain connections, I think these are at least three big areas of potential applications, yeah. Thank you.
Thank you. I would like to say that for me it is important, because when I prepared the book, I had just two pictures, you see, and if you have basis of high-level pictures, then it's possible to make, I didn't say today about image analysis, but that is done, and after how to work, and we have a basis of picture, you see, and maybe like in supervised on unsupervised learning. So it's a great work which may be done with a good base of picture. So thank you very much.
But you see, with the picture, with the images, at least my story was that, okay, you have some method to do something, and then you get some original images. And of course, the images are challenges by itself. And it happened to me a few times that the images basically guided me what to do to solve the problems in the images. So the more images you process, somehow the method is getting more and more advanced and refined.
Yes. Yeah, okay. Thank you.
Well, I think that there is end of the discussion. So many thanks for your talk. It will be recorded, so maybe I think that people who were not present at this seminar will see it, and then there is a contact to you, so there will be not a process to enter into a discussion. So, Professor Mityushev, many thanks for your talk. Many thanks for contribution to Sano Seminars. Thank you very much.
Thank you very much. Thank you.
And I would like to invite all of you to next Sano Seminar, which for many reasons will be not on Monday, but will be on coming Friday at 10 o'clock. On the Sano website, there is information about what will be the topic and whom. We will have a guest from Sheffield at Sano, and this is one of the reasons why this lecture will take place on Friday, not in Monday. So many thanks, and see you on Friday. I understand that not everybody will be able to take part in this because of its date, but anyhow, you are kindly invited. And so thank you very much and goodbye.